Today we're talking about functions in the real world. You have spent an awful lot of time learning how to write equations, how to solve, how to graph them, and even how to compare them. In this lesson, we're going to take all the skills you have to create functions from context and apply your knowledge to actual situations that can occur. And we're going to jump right into our first situation, where the starting balance of Anna's account is $1,250. She takes $30 out of her account each month. We're asked to find how much money is in her account after 1, 2, and 3 months, and to find an explicit function to represent the balance in her account at any given month. We're going to start by looking at some of the important information we were given in the context, like Anna having a starting value of $1,250, and the fact that each month she's taking the same $30 out of her account. And with a constant rate of change like that, we can be confident that we have a linear situation on our hands. Now, some of you will be able to go ahead and write this equation straight up, but for those of us who need a little more guidance, we're going to start off by creating a table. We know that after 0 months, or at the start, Anna has $1,250 in her account. And every month, if she's taking money out of her account, we have to subtract $30 every month. So after 1 month, Anna's going to have $1,220 in her account. At 2 months, $1,190, and after 3 months, $1,160. Since I've subtracted $30 from her account every time 1 month has passed. And the first question we're asked actually has to do with how much money at 1, 2, and 3 months, so that has to be part of my solution. Make sure that if there's more than one question that you're asked, that you're answering each and every question. Now, to write an equation from a table, we paid attention first of all to the amount of change every time we advanced from y value to y value or from x value to x value. We know that our x amounts are increasing by 1 each time we go from row to row. But our y values are changing by -30, right? We're taking 30 out of her account every month. Well, slope is change in y over change in x. So that means I take the -30, the $30 we're subtracting, over 1, and I get a slope of -30. The y-intercept, or b, comes from where x is 0. So we have our starting value of $1,250, that's our y-intercept, and our slope of -30. And we're going to use slope-intercept form, which in my opinion is the easiest of all linear equations. And I'm going to plug that slope in for m and $1,250 in for b, or my y-intercept, and I get f of x equals -30x plus $1,250, where x, of course, represents the number of months that have passed. Notice I wrote it in function notation because we're asked to find an explicit function. Make sure to pay attention to detail. In our next situation, we're asked to consider that the first figure in our diagram has two 180-degree angles, one on each side of the line segment. So we have an angle above and one angle below. Every time we advance one figure in our diagram, each of the angles is bisected, meaning that they've been cut in half. And this pattern continues, and we have the first 4 figures in the pattern below. We're asked to write an explicit function to represent the relationship between the figure number and the number of angles in the figure. By figure number, we mean figure 1, figure 2, 3, and 4. And of course, we can see and count the number of angles that each figure has. So to start with, I'm of course going to create a table. if I take each figure number in my diagram and count the number of angles that are there, our first figure had 2, the second has 4 angles, the third figure has 8, and the fourth figure has 16. When I look at the rates of change, our x values, of course, we're still just adding 1 each time, but on our y values, we're multiplying by 2 this time instead of adding a specific number. That means that our starting value is the 2 angles in figure 1. So our rate of change is 2, and our starting value is also 2. When I use an exponential equation form, a times b to the x power, a is our starting value, 2, b is our rate or our multiplier, which is also 2, and x is going to represent the figure number. So I'm going to put all of our values into the equation, of course writing it in function notation, and I should be done. But this time we're going to take a second to check and make sure our equation works. If I look at figure number 1 that had 2 angles, and I substitute 1 in for x in my equation, 2 to the first power is 2. Multiplying by 2, I get 4, not the value I wanted to have, which was 2. This equation doesn't quite work. The reason being, our starting value was not a true x-intercept because the x value was 1, not 0. I can easily remedy that, however, right? What I want for my x values was 0, 1, 2, and 3, not 1, 2, 3, and 4. I can get the values I want if I subtract 1 from every x value. That gives me a true y-intercept at 2. Well, if I do that to get the appropriate x values, I need to reflect that change in my equation. I can do that by simply putting x minus 1 as my exponent instead of just regular old x. Watch out for situations like that where you don't have a starting value where x is 0. And in our last situation, a video arcade charges an entrance fee and then charges an additional fee for every game played. The entrance fee is $5 and each game costs an additional $1. We're asked to find the total cost for playing 0, 1, 2, or 3 games and describe the total cost with an explicit function. So looking at our table, we're going to put in everything we know. If I don't play any games at all, I still have to pay the $5 for getting in the arcade. If I play 1 game, I have to add $1, so I pay $6. For 2 games, we pay $7, and for 3 games, then we'd pay $8. That actually gives us the answer to the first question we're asked, which is find the total cost for playing 0, 1, 2, or 3 games. Make sure that that makes it into your solution. Then to find the explicit function, we need to look at our rates of change. In the x column, we're adding 1 every time we advance from x to x. And in the y column, we're advancing 1 every time we advance from y to y. To find slope, change in y over change in x gives us a slope of 1, and where x is 0, I can find my y-intercept, which is 5. Notice that my x value is truly 0 this time, so there won't be any adjustments I need to make in my equation. And then using slope-intercept form, writing it in function form, of course, f of x equals x plus 5. Technically that's 1x plus 5, but of course 1x simplifies to simple old x. And x is the number of games played. To wrap up today, don't forget to find the rate of change up front. preferably using a table or something if you struggle with finding that rate of change. If your rate of change is adding the same amount each time, you use a linear function. And if your rate of change is a multiplier or multiplying by the same value each time you advance from y value to y value, you have an exponential function on your hands. When you find the y-intercept, make sure that the x value is 0, otherwise you need to do a little adjustment and reflect that adjustment in your equation. And of course, use the correct equation form. I recommend slope-intercept form for linear functions, and of course our exponential form for exponential functions. I think that's enough for today. Don't forget you can rewind and go back and watch examples again if you need to. But otherwise, I'm going to wish you a great day, and I'll see you next time.